are in Introduction to Statistical Learning, Chapter 8. We're in the implied questions, and we're on question number 9 here. Okay, so we're going to be looking at a data set called OJ, and it's in the ISLR2 package here. So here's all the pieces, and we'll go through them one at a time rather than reading them all up front. But the first thing that we need to do is to create a training and test data set. Okay, so that means we need to load some packages, the ISLR2 package, and then later we'll use the tree package for some of the things that we'll do. So we run that, and then we're going to create our test and training data. So I call up the OJ data set, and I'm going to use 80% of the data for the training, and the rest will go to test. And so what 80%? Well, I'm going to randomly generate an index with this line right here that will, just randomly pick numbers between 1 and the number of rows in the data set. And then whatever row happens to be one of those indexes becomes the training set. And then I just further partition this into X variables and a Y variable, predictor variables, and outcome variable. And then everything that is not in the training index becomes part of the test data, right? So minus the training index becomes the test data, and I get an X and a Y. Okay, so next we are going to fit a tree to the training data, where we have purchase as the response variable, or the outcome, or the Y variable, or however you want to think about it. And then we'll use the summary function to produce some, to learn some things about the tree. So this is pretty basic. So I'm just calling this first model here M, and so I use the tree function, which again, it's part of the tree package, and I just regress purchase on everything. Okay, and I'm using the train D, the training data set for that. Okay, and then I'll call summary M, and we get all sorts of things here with summary M. So it tells us, what we called, the formula we called. It tells us how many residual nodes there are at the bottom of this tree. But we'll visualize the tree here in a second, so that makes a little bit more sense. So I'll tie it back in, and then we get some other things. But another important one here is the misclassification error rate. So there's 136 misclassifications here. Okay. So there you go. 136 out of 856. Okay, so that's that's what's going on in the summary function here. So next in part C, let's just see what happens when we just type M into the line there. We get kind of a detailed verbal description of what the tree would look like. I think that we'll look at what the tree looks like here in a second. So in fact, let's just do that. So we're going to create the tree right here and then tie it back into what we've been looking at so far. Okay, so when we use plot M and then use text M to label the different components of the tree, we get this image right here. And so let's look at this. So the first thing I want to look at is the number of terminal nodes up here that we for B. I mentioned that we'd look at that. So there should be 9 terminal nodes down here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So in other words, as we go down this tree, and the tree is making decisions based on the predictor variables, where to classify a particular observation, eventually it grounds out in 9 different, terminal nodes here. Okay. Now let's try to understand what happens when we just type M into there. Okay. So the first thing we notice is that we get the output tells us that when we get this asterisk, is it asterisk or just asterisk? I don't know. I'll say asterisk. I think that's correct. That signifies a terminal node here. Okay. So each one of these lines here is representing one of these terminal nodes in the tree. Okay. So there should be 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Good. and they're also arranged hierarchically. Okay, so you can see this pattern of indenting, and that pattern of indenting is taking you down from higher to lower levels of the tree here. Okay, but let's just read one of these lines here, what it means here. Okay, so let's look here at 2. So we have the predictor variable that has been selected to make that first choice, whether we go left or right, down the tree here. And so you can see that right here at the bottom of your screen, loyal CH. And then it gives us the split condition less than 0.5036. Okay, right there. Also, I've detailed what I'm saying right here in these bullet points here. Okay, and then it gives us the number of observations that fall within within a particular branch. Okay, so 369 fall within going, that are less than 0.5036. Okay, and okay, what's next? So 4.3 or 433. This is the deviance. We're not, I don't think that the book really discusses the deviance very much here, but that's the deviance measure. And then finally this MM here says the overall prediction associated with this branch. So I believe that it must be that 27% don't go to MM and 72% do go to MM. Now, of course, this isn't this first branching here is not a terminal node, and so I'm not, that doesn't mean, well, it means after we filter all the way down that, then the observations roughly partition like that. Okay, so but let's look at a terminal branch now. Okay, so we go down. So let's look here at this terminal branch. Okay, so again we have the variable and the split condition. So loyal CH less than 0.03. Let's see. So we're down here at this branch right here. Okay, oops, right there. And okay, what's next? So we have 65 observations fit that criteria. So here we have the deviance, and then the output is MM. Okay, and then for and then these are the relative percentages for going on either side of the branch. Okay, so hopefully you can see how that all runs, or interpret each of these. But of course, just looking at the tree is easiest. Okay. Okay. Part E here. So predict the response on the test data. So all of this was on the training data, and of course, often what we want is how our model performs on things that it has not been trained on. Okay, the test data. So that's what we're doing here. So we're going to predict what happens with the model and when applied to the test data. Okay, and then we're asked to create a confusion matrix, and there's a very simple way of doing that in R, just this table command right here, and you'll see what it looks like. And so let's look at that. Okay, so what we have here is where what is predicted versus what is actual. So 117 times when CH was predicted, we got CH. 60 times when we predicted MM, we got MM. And then these off diagonal terms are when we, guessed CH but got MM, or guessed MM and got CH. Okay. Now we're supposed to compute the test error rate, and so that would be, very simple. We just sum these guys up. Oops, these off diagonal terms divided by, the total number. And I guess I really didn't do that here because with each run of this, you get, depending on how the data shakes out when you randomly generate your test and training data set, you get different numbers, and so this matrix will change. And so putting something in text, I think, could be misleading, but hopefully this makes sense here. Okay. Okay. So now for part F and G, so we're going to apply we're going to cross validate. So we're going to use CV tree to the training set to determine the optimal tree size, and then we're going to produce a plot, you know, demonstrating this. Okay, so we have CB tree, and so I'm using M, and then I'm going to prune. I'm going to prune the tree, and then we're going to plot the different levels of deviance, and you can just think of deviance as how well the model is not doing. Right? More deviance means worse. Okay, so we do that, and in this particular instance, we get that the best model is in fact 9 terminal nodes. Okay. Again, depending on how, what happens when you are randomly dividing the data and some other stochastic processes in this whole workflow here, you will get different numbers. So I'll often see 5 or 6 or 7 and sometimes 8 or 9. So in this particular instance, it was down at 9. So okay. So now we want to take this information that we just used, and we want to find the best size of it. So visually, we see that it's 9 here, but I want the computer to tell me which entry is the best one, and so this is the line that I'm using for that. Okay, so you can dissect that line for yourself, but this should say 9. Okay, so it's 9 terminal nodes. Is the best tree here. Okay. So again, all that's doing is just verifying what we see visually here, and then it allows the computer to pick that out rather than us having to type in 9 each time as we go down. Okay. So now we're going to produce a pruned tree with the optimal tree size using best size here. Okay. As we obtain through cross-validation. And apparently this might fail sometimes. I haven't seen it fail, but if it fails, you're supposed to just use 5. Okay, so we run that, and then we have our similar construction, our this guy right here, but applied to the best tree size, which is 9. So these actually should be identical, right? Because up here we had 9 terminal nodes, and the best we can do apparently is 9 terminal nodes on the test data, according to this run. Again, if you run this again, you'll likely get different results. So, okay, so now we're going to compare the training error rates between these two. So I'm just going to use the summary function here, right? And if you remember the summary function right here, produced this from which we could get the misclassification error rate. Now we can pull out the misclassification error rate by, asking it to return misclass. Okay, and so we get this. Okay, so again, the trees that we produced were identical, the best and the incidental one, or whatever you want to call it. And so in both cases, we get 136 errors out of 856 total observations in both cases. Again, the fact that these tied, or these particular numbers, will vary depending on the run that you're using. Okay. And then we're going to compare the error rates. Okay. So on the test data, so this was training data. So earlier, before we used the prune tree, right? Before we used the prune tree, we did this, right? And we could calculate the error rate, by taking these off diagonal terms, and taking that as a numerator, and then the total as the denominator. Okay, so we'll just do that for both tables. So now I need to predict the test data given the best model, the best tree, and then I'll just compare the confusion matrices here. Okay, and again, because these models happen to be the same, we get the same output here. Okay, so I hope that was clear, and we'll call that good.